So when Farhan proposed this seminar, he said, we could see techniques that we don't usually see. And I instantly thought of this, even though it's totally useless and you'll never use it anywhere. But I just wanted to talk about it anyway because I think it's kind of fun. Okay, so maybe you've seen Riemann's rearrangement theorem. It says that if you have a conditionally convergent series, you can rearrange it to converge to anything you want. That's basically what it says. So has everyone seen this before? Yeah, for example, I guess the most famous series is the alternating harmonic series, 1 minus a half plus a third, so on. And maybe even some calculus books have an example of how you can rearrange it and get like 1/2 ln2 instead of ln2. I'll be saying permutations are the bijection between n and itself, and I'll be saying rearrangement for the actual series. And we could say a lot more. For example, you could say you can make it diverge to infinity, or you can make it diverge by oscillation. You can make it do whatever you want, but we'll just say that this is Riemann's rearrangement theorem for now. And the proof idea is, since it's conditionally convergent, basically you have a bunch of positive terms, a bunch of negative terms. The positive terms converge to 0 as a sequence, and the negative terms converge to 0 as a sequence. So given any real number L, let's say L is 10 or something. Well, whatever, I said L is 0. Okay, so if L is 0, for example, start with the first positive number. Then add consecutive negative numbers until you're under 0. So add negative numbers until you finally reach a negative number. Then add positive numbers until you get over 0. Keep doing this, so you're going to kind of oscillate around 0, but the terms converge to 0, so the rearrangement will converge to 0 as well. Right, so I guess the fact that they, as a sum, go to infinity means that you're guaranteed that no matter what negative number you're at, for example, you could sum back up to 0 and past 0. So this algorithm doesn't really provide an explicit permutation. All it says is add negative numbers, add positive numbers. Right, so you can't really write it down. And maybe for some reason, like I said, you probably won't use this anywhere, but you might want an explicit formula. So that's kind of the goal today. So one question you can ask is, can we find simple permutations of the natural numbers such that we can easily compute the rearrangement? And in general, I think this is a hard question, although I'll mention something else about it. But we'll just stick to the alternating harmonic series today, because it's very nice to work with. Okay, so there are some answers to this question. For example, although it's not, we still don't have an explicit formula for the permutation. There are some nice cases where you can explicitly get an answer from some given permutation that's somewhat simple. So if you add n consecutive positive terms, then n consecutive negative terms, and keep doing this. So for example, if m is 3 and n is 2, so you add 1 plus a third plus a fifth, and so on. Then the rearrangement converges to ln2 plus 1/2 log m over n. And this, for example, is dense in the reals, so it's kind of the best you could do because there's countably many. But there's no nice formula. And another answer to this question is, in the 1970s, Smith showed that given any conditionally convergent series, not just alternating harmonic, there's a permutation of order 2, which means if you compose it with itself, it'll just give you the identity. So all you're doing is swapping terms. You're taking two terms, swapping them, taking two terms, swapping them. There's such a permutation that rearranges your series to anything you want, including infinity, negative infinity, diverge however you want, whatever. And at least to me, that's not obvious, because all you're doing is swapping terms. This is nowhere near just saying add positively many than negatively many, whatever, until you get the limit you want.
Is there any intuition you can provide?
I can provide some intuition, but it might not be good enough. So let me first say, if you want infinity, the intuition is this. Move out the negative terms really far away. Like send the nth negative term to like 2 to the nth negative term or something. Or not 2 to the nth negative term, but like 2 to the nth positive term. So you're bringing positive numbers close, and you're moving negative numbers really far away. So how do you tell if a series converges? You look at the partial sums. So whenever you look at a partial sum, all you have is a bunch of positive terms and some small negative terms. And then it'll go to infinity.
So it builds up faster.
Yeah, it builds up faster. So that's some intuition. But the intuition for why you could do it to why you can converge to any real number, I guess, is somewhat like Riemann's rearrangement theorem. You want to move big negative terms out, and you want to move positive terms in that kind of make you get closer and closer to this real number. If it's like too big of a positive number, like we said for infinity, maybe you want to move in a smaller positive number. So you could always go far enough out so that a smaller positive number comes in. That's kind of the intuition. But I don't think it's obvious. For example, my advisor, I asked him if such a thing exists. So before like I knew this result existed. And he's like, oh yeah, it should exist. But then I talked to someone else and he's like, I don't know, that's not obvious at all. So I guess it depends who you ask if it's obvious.
So the proof for it, is it sort of constructivist, or is it just like proof by contradiction? Like if that wasn't true, that's Riemann.
His is kind of constructive, but it's kind of clever. You can actually give a very basic proof, like undergrad real analysis epsilons deltas. So I have such a thing, but it's not very fun to read. Yeah, but you can give like a pretty constructive proof, you know where everything's coming from and so on. Well, yeah, it's constructive as long as you know your series, because you need to say, look out far enough so that the positive terms between like 1/2 to the n, you know, so on. So it's constructive in some sense. It's not contradiction, for example.
So what if you know if your AN is the alternating harmonic series, for example, can you construct this phi explicitly? This one, that is order of 2.
I have a partial answer to that question.
Good.
Yeah. So we will consider such permutations with the alternating harmonic series. But I can't give you all of them that make, I can't for any real number give you a very explicit one that says it'll converge to that real number. But we'll consider some of them. So for example, let's look at one of the simplest ones I could think of. So, okay, let me ask you guys. I guess I should kind of go back and just ask your opinion. What's kind of the simplest thing you could think of? This is kind of...
Permutation of order 2.
Yeah. What's one of the simplest permutations of order 2 you could think of? It's not like that easy of a question, I guess, but just if you could think of anything.
All the even numbers.
You could switch all the even numbers? Even with what? So I have an even number and I do what?
Make it out.
Yeah, make it. So that's the simplest one I could think of. But that's it's slightly more complicated because you can't take every even number and do that. What you could do is take an odd number and double it.
Yeah.
But then you get something that's 2 mod 4. So it's a little more complicated. Because otherwise, if you take any even number, you might divide it by 2 and it'll still be even, so it might not be a bijection. So you need to guarantee it's a bijection somehow. And this way, we just double every odd number. So it'll send odd numbers to 4k plus 2, and since it must be a permutation of order 2, it should send that double back to the odd number. And I want to write the shorthand, this double arrow thing, even though I won't use it too much. But it's just kind of easier to look at than this piecewise definition of the permutation. One thing we could do is consider what it does to these little groups of 4 terms of the alternating harmonic series. So every term can be written as one of these guys. So just consider 4 of them. And by considering 4 of them, we're actually considering all of them. So it'll double the first and the third one. It'll half the second one, and it'll do nothing to the fourth one. So if we could group terms in the rearrangement, so if we can group these guys and just take the sum over k of this, then that'll give us the same sum, if we're allowed to group. We are allowed, actually, in this case. Yeah, so we learned we're not allowed, but we are allowed. Depends when. So let me just convince you that we considered all the terms, like that this is actually enough to compute it. So what we did is take an arbitrary term of the alternating harmonic series and look at what happened to it. So actually, we are considering all the possible terms in the new series by considering these 4 blocks, this block of 4. We need to know some facts first. So if we look at the sum from n equals 1 to big N of the harmonic series, then that equals to ln of big N plus gamma, which is the Euler-Mascheroni constant, plus big O of 1 over n. So then as we take n to infinity, the big O will go away. So first, we can kind of mess around with this. We could split up a partial sum into its odd and even parts. And we know what this converges to by the top fact, because this is just 1/2 of that series, except now it goes to n plus 1. It starts from k equals 0, I shifted it. So there's an n plus 1 in the answer. So from here, we know what this is by the top, so we can subtract and get what the odd ones converge to, or how the odd ones behave. So the odd ones behave like this. And I don't even really need the n plus 1. I could just move it into the big O of 1 over n, but I wrote it like this. And similarly, we could say n equals 1 to 4n plus 4, break it up into the everything mod 4, and then do something similar. You'll get 1/4 of 1 over k plus 1. You can compute that. You'll get 1/2 of 1 over 2k plus 1. You can compute that. So you can compute the other two. And what happens if we go back, we needed the sum of, we needed what this one converges to. If we're just take a partial sum, we want to know how this behaves, how that behaves, how these two behave. So these two are 1/2 of 1 over 4k plus 1 and 1 over 4k plus 3. And then this is something we had and that's something we had. So let's just look at what happens if we take a partial sum. If we take a partial sum, if we're allowed to group and take a partial sum like this, we know exactly how it behaves. So if we're allowed to group, the new sum will be 1/4 ln2. I didn't rewrite everything from the last slide, but I promise this calculation is correct. All the gammas canceled in particular. So there was a gamma here. All the gammas canceled because you ended up having like 1/2 gamma minus a 4th gamma minus a 4th gamma, something like that. So all the gammas canceled, and we just get 1/4 ln2 and then just some big O of 1 over n term. So as n goes to infinity, we get 1/4 ln2. But we actually have justification why we can group terms in this new sum. Here's a proposition. We can group terms as long as the terms go to 0. We can group terms in a fixed number of blocks like 4, not an increasing number of blocks or whatever, in a fixed number like 4, and then we could take the sum when the terms go to 0. So that's why you're not allowed to group 1 minus 1 plus 1 minus 1, whatever, because they don't go to 0. But if they go to 0, you're allowed to group. And
If they change sign?
yeah, they go to 0. So what happens is you're looking at the partial sums. So what this partial sum really is, if I'm grouping into these blocks, then I'm looking at partial sums of the form sum up to n times little n of ak. I'm looking at this sum. So this is a subsequence of my partial sums. Well, there's a theorem that the Cauchy sequence, if you have a complete metric space and a subsequence converges, then the actual sequence converges. And the other way, if a sequence converges, all the subsequences converge. So it's an if and only if statement. Or you could not use this theorem and also just prove this with epsilons deltas. Because eventually, for high enough big N, since little n's fixed block, just make sure all of these terms are less than epsilon over n or something, and then it's easy to see. So the way that, the right generalization, I think, of what we did is taking something that's B mod A and sending it to something D mod C. So let's see if we can compute these. Here's a theorem. So we want to look at the alternating harmonic series. Just as a convenience, I want B to be between 0 and A. I can't have it be 0 or else it won't be a permutation. But it could be bigger than A, is just for convenience. And also, this guarantees that it's that what I'll have is a bijection. So it's also an if and only if. It's a bijection if and only if this thing holds. And if we define this permutation, which is just a more rigorous way of writing switch AK plus B with CK plus D. So I had something AK plus B, I subtracted B, I divided by A, so I get K, I multiply by C and add D. So AK plus B went to CK plus D. And CK plus D went to AK plus B. And all the other terms are not moved. Then phi is a bijection, and the new sum converges to that thing. So even though this is not too easy of a formula, the permutation is really simple, and at least it's explicit. And we could say some stuff about the rearrangement. So let's see what happens. Every rearrangement switching AK plus B and CK plus D converges, because this is a real number. And you could check it could actually be as big as you want and as small as you want, just by plugging in C equals like 2 to the n or something, and A is 2. If A and C are odd, the sum doesn't change, because these have opposite signs. So if B is even, then A plus B is odd. And if B is odd, A plus B is even. Same thing with C and C plus D and D. So if A and C are odd, the sum doesn't change, which is really strange. For example, if you were to triple, that sum wouldn't change. But the doubling one changes. And there's another way to see this, but we won't talk about that. If you look at the partial sums, a lot of stuff cancels out. Another thing you could see, you need to prove it, but reals of the form above with the divisibility conditions stated are dense in R. So it's the best we can do. Even though somehow a lot of them even stay the same. Another thing we could say is that it never equals 0, for example. It's not trivial to see. You kind of need to do something, but this quantity starting from ln C over A is never equal to minus ln 2. Okay, so the one thing I want you to get out of this talk is how to work with rearrangements. Again, I don't see any reason why anyone would work with rearrangements of a series. But if you work with rearrangements, I think this is the right idea. If you look at partial sums up to big N, what you want to do is look at the terms that get moved far away, that get moved out, and you want to look at the terms that get moved in. So to do that, I think abstractly the best thing to look at is this difference, the difference of partial sums. And you could write it as these four sums. So the terms that get, which terms will get moved out, which terms will stay, yeah, and which terms kind of don't matter because they're not in here, they're not permuted by, they are, what should I say? The terms that are here are also here because phi, anyway, these are the terms that got moved out. These are the terms that got moved out. And on the very right are the terms that got moved in. And you could simplify that to the following. Because these terms didn't get moved far enough away. They just cancel with what was already there. So all you have is the difference of the terms that got moved away minus the terms that got, you got the terms that moved away, and you had the terms that stayed. That's all you care about. Anyway, I think this is kind of the main idea for rearrangements. But we won't be using it too explicitly. One other thing I want you to get out of this talk. Yeah.
We will analyze this sum.
We'll have a sum that's similar to something like this at the end. So we'll have the alternating harmonic series, and we'll have the rearrangement. And although I won't do it explicitly, it would be easier if we subtracted them and then looked. But yeah. Another thing I want you to get out is some properties of the Digamma function. We've seen the Digamma function in last year's seminar. It came up at some point when Catherine was talking. So the Digamma function is this weird thing. It's the derivative of log gamma, where gamma is the standard gamma function. And it has some very relevant properties. Let's see what they are. So, although you might not see rearrangements very often, two big names in analysis at least cared about the Digamma function. This is the Jensen you know and the Grunwald you know. So Grunwald and Jensen wrote a nice exposition about the Digamma function in 1916. So one relevant thing is if we look at this sum, this partial sum, we have some nice formula. We don't know what digamma of B over A is, but we have some nice formula. It behaves like log x at infinity. And it has this other useful identity. This is a sum from p equals 0. We'll see this near the end. So we had this rearranged series. Why did it even have a chance of converging? So this will answer the question. And why do these sums, period, in the theorem have any chance of converging? So if we have some numbers, I'll write them as Ci over Ai. If the sum equals 0, then this sum of terms converges, and we know exactly what it converges to in terms of digamma. And it converges, sorry, I should say absolute, that should be absolute convergence. What happens is if the sum of Ci over Ai is 0, if you just add these up, so have a common denominator, what will happen is you'll get something in the denominator that's degree 2 higher than what's on the top. So it has to converge, because you can compare it to like 1 over n squared, which converges absolutely. And we get this formula because we use property 1, and it turns out all of the guys on the top cancel. Because it behaves like log, and when you add them all up, you again use this property that Ci over Ai, the sum converges to 0, and then all the logs just go away. We didn't do this for the first example, the doubling, but it would have been much easier because a lot of stuff would have canceled. But in our case, we would have actually had to know what digamma is at like 1/4 and a half, which was kind of a problem. But if I actually looked at a block of 8 terms, then I wouldn't have to know any values, and everything would just cancel by using property 3, and we get something very explicit. We will somewhat make use of the main idea. What we want to do is look at partial sums, but we want to look at the sums up to 2ACN. We need it to be even, and for some reason, we need it to be divisible by AC, or else somehow we're not considering all the terms. For example, in the last one, A was 2 and C was 4, and we only looked at blocks of 4, not 8. But it turns out in general you need something like 2 GCD of AC or something, or else you're not considering all the terms. I found it just easier to write AC everywhere instead of GCD. we can write this partial sum as this sum. So this is just looking at blocks of 2AC. So if we fix k equals 0, then this goes from 1 to 2AC minus 1. And then we take k equals 1, it starts at 2AC. So we're really considering all of them. We're stopping at 2AC minus 1, then starting at 2AC. Then stopping at 2AC times 2 minus 1, starting at 2AC times 2, so on. So all I did was rewrite a finite sum. And we want to split it up into terms that get moved away and the terms that stay inside. So what will happen is we'll have the terms that get moved away. We can apply the permutation explicitly to them because we know it explicitly for those terms. And the terms that were brought inside, we know where they came from. So we'll be able to write those very explicitly as well. So we want to split it up into these things. So we want to see which ones are B mod A. There are 2C of them. So you can see that these are B mod A. And I promise you that that's all of them. And there are 2A terms that are D mod C. And then there are the rest. So the rest are just whatever was in here subtracted what we took out. Let's keep in mind that what we considered on the previous slide, we had 2ACK plus NA plus B. That's going to be moved to 2C squared K plus NC plus D. All we did was replace each A with each C and each B with each D. And that'll make sense. Because, okay, so if we do it explicitly, we subtract B, we divide by A, we get 2CK plus N. We multiply by C, we get the C squareds and the C, and then we add D. And the same thing for the other terms. So if we rewrite the rearrangement in the following way, so we're allowed to group. What I did was group 2AC many of them. I'm allowed to do that since the terms all go to 0. And then I just rewrote it as the terms that were permuted. So we took, in the original sum, we had 2ACK plus NA plus B. That was permuted. If we apply the permutation, it'll turn into this. To the other guys, if we apply the permutation, it'll turn into that. And then the rest, nothing happens. And these were the rest. Now we use our other result. We needed these. We needed the sum of the Ci over Ai to be 0, where the sum we were considering is C1 over A1k plus B plus Cn over Ank plus Bn. We needed the sum of the Ci over Ai's to be 0, so we need to check. We need to check that these leading coefficients of all of them sum to 0, or else we can't apply the proposition. So if we just check, if A is even, NA is always even, so these have the same sign no matter what N is, and there are 2A of them, so you'll get 1 over A or a negative 1 over A. And here you'll get the opposite sign, but there's 2C of them, so you'll get 1 over A times the opposite sign. It'll sum to 0. This is just something to check. It looks complicated because there's a lot of NAs or whatever, but it's easy if you're not just, if you have a piece of paper out, it's really easy. The same thing happens with the other terms. And the last ones just sum to 0. So these are the 5 different coefficients we had. Since each of these separately sum to 0, then they all sum to 0, so we could apply the proposition. So it converges uniformly, and we can use the other proposition. We can use, let's go back to this one. So we're going to use this, then the sum converges to sum of digammas. And it looks like there's a bunch of crap here, but it'll all cancel. So if we just use the formula, and for now, I'm going to forget about this one, because this was just the original. If we sum these from k to infinity, this will just give you ln2, because this was the original broken up alternating harmonic series. So this is going to be ln2, and just forget about it. This will give us ln2. So let's consider the other 4. The other 4 are going to sum to this complicated thing because we don't know what digamma is. It's too hard to figure out. But let's just consider one. So one of them, if we rewrite it a little bit, so you need to split the odd and even ones, we get a sum from n equals 0 to c minus 1. You can compare with this formula. So we have some q. This is going to be q in our formula. P is going to be n, and c is m. So if we just use the formula on this new expression, we could figure out what it converges to. We're going to apply this property, and it'll give us something kind of complicated, again, because we don't know what digamma is. But if we take all of them, 1, 2, 3, and 4, then everything cancels. All the digammas cancel. This d over 2c cancels with that one. This d over 2c plus 1/2 cancels with that. These guys cancel, these guys cancel. All we have are logs left over. And we know more or less we're more familiar with logs. So adding them all up, we get the right side of the formula for the theorem. And we also had an ln2 that we weren't considering. We get the formula ln2 plus the rest of that. And you could generalize this slightly by considering permutations of order n. As long as it's a bijection, you have similar divisibility condition, you just do the same stuff, and you get something similar. I don't know if it's a theorem. It's more like a silly calculation, but it was fun to do. Yeah.
Was this just something you did out of curiosity, or was this part of like a bigger thing?
It's not part of a bigger thing. My friend and I talked about something, and this kind of came up. The original question was, can you make permutations of order 2 sum to anything? So we worked it out, but it turns out it was done already. So instead, did that.
And is it easy to see that this expression is dense?
You need to. There's some epsilons and deltas to take, but if you just do it out, it kind of works itself out. Like you need to, there's some like number theoretic stuff going on. Like you need to do something like take C to be like 3 mod 6, for example, works. You can't just double and see that it's dense. You need something a little more complicated. If you take C to be like 3 mod 6 and A to be something else, then you look at E to this expression, and then you could kind of see, you could see something. I wouldn't say it's obvious. Maybe it'll take a page and a half to work out epsilons and deltas. Basically, the idea is this. Let's say at least if you want it to converge to 100. Yeah, so kind of the idea is you need to balance this ln c over a with a 2a. So you want it to converge to somewhere close to ln c over a, which we know is dense in the reals. At least from this other result, we said those are dense. It's easier to see that these are dense in the reals. Then we kind of want the 2a to not really affect it. So say we want it to converge to 100, then take ln c over a to be somewhere like 200. Then this is like, or whatever, 400. Then this is like going to divide it. And then you want c to be so big that this term is like less than epsilon. And it just works out.
All right, thanks, Max.
Thanks.